Breaking down salts, chemistry of desalination. Breaking down salts, the chemistry of desalination. Water, an essential resource for life, covers about 71% of the Earth's surface. However, the majority of this water is saline, rendering it unsuitable for consumption or most industrial processes. As freshwater resources become scarcer due to increasing population and climate change, the process of desalination has gained prominence as a solution to the growing water scarcity problem. Desalination is the process of removing salt and other impurities from seawater or brackish water, making it suitable for various applications. This article delves into the chemistry behind desalination, exploring the mechanisms of different desalination methods and their environmental implications. Understanding salts and salinity. Salts are compounds formed by the combination of a positively charged ion, cation, and a negatively charged ion, anion. The most common salt found in seawater is sodium chloride, NaCl, also known as table salt. However, seawater contains a multitude of other salts, such as magnesium chloride, MgCl2, and calcium sulfate, CaSO4. These salts contribute to the overall salinity of water. Salinity is typically expressed in parts per thousand, ppt, or practical salinity units, SU. The average salinity of seawater is around 35 parts per trillion, meaning that for every 1,000 grams of seawater, 35 grams are dissolved salts. This high salt concentration makes seawater undrinkable and unsuitable for many industrial processes without proper treatment. Desalination methods and their chemistry. Desalination processes can be broadly categorized into two main types: thermal-based methods and membrane-based methods. 1. Thermal-based methods. A. Multi-stage flash distillation, MSF. This method involves heating seawater in multiple stages, causing it to evaporate. The vapor is then condensed to produce fresh water. The heat needed for evaporation is usually obtained from steam generated by burning fossil fuels or utilizing waste heat from industrial processes. This makes MED more energy efficient than MSF. C. Vapor compression distillation, VC. VC uses mechanical energy to compress vaporized water, increasing its temperature and pressure. The high-temperature vapor is then condensed to produce fresh water. The compression is typically achieved using electrically driven compressors. 2. Membrane-based methods. A. Reverse osmosis, RO. In RO, seawater is pressurized and forced through a semi-permeable membrane that allows only water molecules to pass while rejecting salts and other impurities. The pressure applied must overcome the osmotic pressure to facilitate the separation. B. Electrodialysis, ED. ED involves passing seawater through a series of ion exchange membranes. An electric field is applied, causing positively charged ions, cations, and negatively charged ions, anions, to migrate through selective membranes, leaving behind desalinated water. C. Electrodialysis reversal. ED is an advanced form of ED where the polarity of the electric field is reversed periodically. This helps prevent membrane fouling and increases the efficiency of ion separation. Chemistry behind the process. This separation is achieved by exploiting the differences in boiling points and vapor pressures of water and salts. As the water molecules evaporate, they leave the larger and heavier salt ions behind, resulting in freshwater vapor. When this vapor is condensed, it returns to its liquid state as fresh water, leaving the salt ions behind. In membrane-based methods, the chemistry revolves around the principles of selective permeability and ion exchange. In reverse osmosis, the semi-permeable membrane acts as a barrier that only allows water molecules to pass through, while rejecting the larger salt ions and impurities. The driving force is the applied pressure that overcomes the osmotic pressure, forcing water molecules through the membrane. Electrodialysis and its variations work based on the migration of ions in response to an electric field. The selective membranes allow only specific ions to pass, leading to the separation of salts from water. Environmental and technological considerations. While desalination is a valuable solution to water scarcity, it comes with certain challenges and considerations, both environmentally and technologically. Energy consumption. The energy required for desalination processes, especially thermal-based methods, can be substantial. Fossil fuels are often used to generate the heat needed for evaporation, which contributes to greenhouse gas emissions. Advancements in renewable energy technologies are helping to mitigate this environmental impact. Brine disposal. Both thermal and membrane-based methods produce concentrated brine as a byproduct, which contains the removed salts and impurities. Disposing of this brine can be problematic if not done properly, as it can harm aquatic ecosystems and disrupt local marine environments. Dilution, dispersion, or treatment of brine before disposal are strategies being explored to minimize its impact. Membrane fouling. Membrane-based methods are susceptible to fouling, the accumulation of impurities and deposits on the membrane surface. This reduces efficiency and necessitates frequent cleaning and maintenance. Research is ongoing to develop more robust and fouling-resistant membranes. Innovation in the future. The field of desalination continues to evolve, driven by technological advancements and the increasing need for sustainable solutions to water scarcity. Researchers are exploring new materials for membranes, improving energy efficiency, and investigating innovative desalination approaches, such as forward osmosis and pressure-retarded osmosis. Mitigating environmental impact. Efforts to minimize the environmental impact of desalination are crucial to ensure the long-term sustainability of freshwater resources. Researchers and engineers are actively working on several fronts to address these challenges and develop more eco-friendly desalination processes. Renewable energy integration. One promising avenue is the integration of renewable energy sources, such as solar and wind power, into desalination processes.